Hello class, this is Professor Gavor, and I want to cover the first chapter of Introductory Statistics, Sampling and Data. There's 4 sections in this chapter. Definitions of statistics, probability and key terms, data sampling, variation in data and sampling, frequency tables and levels of measurement, and finally experimental design and ethics. This chapter is mostly about definitions and getting some terminology straight. They're all terms that probably you know something about, but maybe don't define them exactly the way statisticians define them. I don't know, they have chapter objectives. It's odd for a professor to say this, but I guess these are my objectives: recognize and differentiate between key terms, apply various types of sampling methods to data collection. We don't really do that very much in this class. We talk about it a little bit. And create and interpret frequency tables. That for sure we will do, and there'll probably be a separate video on how to do that in Excel. In this course, we have decided that we're going to use Excel as our statistical package primarily for the whole course. In other courses at North Park, they've used the TI 8384 calculator series, but not everyone has it, and they're expensive, another $100 in class fees basically to get one. And one thing that is for sure is that when you get, after you graduate and you go to the workplace, and if you're doing any statistics at all, no one uses a TI 83 or 84 calculator. They're using Excel, they're using SPSS, which is a specific statistical package, or more and more they're using the open source statistical package based on Python, which is called R. So what is statistics? Well, it deals with collection, analysis, interpretation, and presentation of data, but it also uses that collection, analysis, interpretation, and presentation of data to help us make better decisions. I mean, why are you collecting data? Just to analyze it, to interpret it, to present it and show people? Yeah, you might want to do that, but the whole purpose is to be able to make better decisions. So the first thing you can do is organize and summarize the data. We call this descriptive statistics. We summarize by using tables of numbers, but as you've probably heard the old saying that a picture is worth 1,000 words or a picture is worth 1,000 numbers, graphical display of data can really help enhance the understanding of what's underlying. And you know, you've heard the Mark Twain quote, there's lies, damn lies, and statistics. Well, we're going to try to not live up to Mr. Samuel Clemens or Mark Twain's description of statistics, and show you, maybe hopefully make sure that you don't use it in a misleading way. Okay, once we add and talk about probability distributions, we're going to do something else called inferential statistics. That we want to take the data that we were given or we've collected or we've gathered and manipulate it, do some mathematical calculations, and draw conclusions from it. Basically help us make decisions. This is where you don't just describe what's going on, and descriptive statistics can help you make a decision, but inferential statistics is even a more powerful tool for making decisions. So probably the first third of the course is descriptive statistics, maybe the first quarter, and the rest of the course is about inferential statistics. As I've told students before, you know, statistics, the reason students have trouble with it is to fully understand what we're going to cover requires more mathematics than you have. If you look at, I took an Introductory Statistics course uh, almost 50 years ago. I kind of could do the problems, but I did not fully understand what I was doing. I took a couple other Introductory Statistics courses in the course of my undergraduate work career and then graduate school. I never really understood statistics. Finally, I said, I'm a mathematician. I've got a master's degree in mathematics. Why don't I understand this? So I took a course in mathematical statistics in which we used calculus. All of a sudden, all the lights, everything clicked because I had the deeper underlying understanding of why. It's like I can tell you how to bake a cake, 2 eggs, a couple cups of flour, some leavening, like baking powder, baking soda, or yeast, or whatever the case may be, sugar, vanilla extract, this, that, the other thing, and you put it all together, put it in the oven, mix it all up, pour it into a pan, bake it at 350 degrees for, 20 minutes or something, and voila, you have a cake. I can teach you how to make a recipe, which is what like teaching statistics at this level is. But I don't understand how the cake works. I don't understand the food chemistry of how leavening agents work and bread and everything mixes together to form, little air pockets and rise and all that. Who knows how that works, but we can still make the cake. So that's kind of how we're teaching this class. I will try to enhance the understanding the best I can. So inferential statistics uses probability to determine how confident we are about the conclusions we're making, and the conclusions we're making are actually those decisions. So first thing, probability. What is probability? It's a part of mathematics that we use to study randomness, random events, and chance. The world is full of random and chance events. Is it going to rain today? Is it going to rain tomorrow? Is it going to rain next week? Are there, we're planning to do this, that, or the other thing. We're forecasting our sales for next month. Will the sales actually be that? Will they be off? They probably won't be exactly what we're forecasting because predicting the future is hard. And so we're taking into account some chance. We're trying to predict the likelihood of that sale occurring. So in the study of statistics, you use the power of mathematics through probability calculations to analyze and interpret your data. We'll use such examples as flipping coins, rolling 1 or 2 dice, which are completely different results and have a different underlying probability distribution. So while we talked about probability distributions in inferential statistics, you kind of have to understand first probability and then probability distributions a little bit. Now, probability can get complicated very, very quickly. What is the probability of getting heads if you flip a fair coin? And I don't know if I've ever seen an unfair coin, but if you flip a fair coin, the probability of getting heads is 50%, or 1/2. The probability of getting tails is 50%, or 1/2. If I flip the coin 10 times in a row, what's the probability of getting 10 heads, or 7 heads, or 6 heads out of that 10 flips? We use cards. Cards are a wonderful way of looking at probability because there's 4 suits, there's 52 cards, 13 of each suit. There's 13 different card values from ace all the way to king, ace being 1. And, so we can always ask, if I pick a card from random from a deck, what's the probability of it being a heart? Well, hearts are 1/4 of the deck, so 13 hearts divided by 52, that's 1/4. But it can get complicated very quickly. What's the probability of getting a heart and a face card? What's the probability of getting hearts, picking a heart or a face card? These become slightly different. And means both conditions have to be met. It has to be a heart and a face card. Well, how many of those are there? There's 4. How many cards in the deck? 52. Good, so 4 out of 52. Actually, there's only 3. Jack, Queen, King. 3 out of 52. What's the probability of picking a heart or a face card? Well, there's 13 hearts. Now it can be either or. I don't care if it could either be a heart or it could be any face card, including the heart. So there's 13 hearts, including the face card, and there's 3 each of the other 3 suits face cards. So that's 9 more. So you had 9 to 13, that's 22 divided by 52. And this can get complicated quickly, and we're going to cover that probably in the next couple weeks. Okay, more key terms. One of the things we look at is the difference between a population and a sample. The population is all items of concern. So we want to study a population. We want to know if we're going to try to predict the presidential election, the population we're interested in is all people who will vote. You could say all people of voting age, but not all people of voting age vote. So you have to be very specific. All people of voting age who are going to vote. And again, talk about probability. We don't know if someone's going to vote or not. We can guesstimate that. So maybe people err on the voting public, the public that is able to vote. Now, I can't go door to door and say, are you going to vote for candidate A or candidate B? Because it's a country of 350 million people. Let's assume 200 million people are qualified to vote. That's a lot of people. It's very expensive. I can't call them. No one answers their phone. I can't send them an email. Only a small number are going to respond. And I certainly can't go door to door hunting them down because that would be an astronomical cost. So what we do instead, we said, can we pick 50 people or 30 people or 100 people out of this 200 million and pick them in such a way that if we ask them who they're going to vote for, the results we get from that sample, a smaller subsection of the population, can we draw the conclusion, extend the conclusion that we get in a sample to the population? We're inferring the conclusion we get in a sample to the population. That's the basis of inferential statistics. Can we collect a small sample, analyze it to death, draw some conclusions, and extend that to the entire population? Now there's some rules and regulations on how we're going to do that, and it's based on the probability distributions that we're going to study eventually. So obviously the larger the sample, the better you're going to do, but after a certain point, adding more sample isn't really going to change the results that much. And surprisingly, sometimes a small sample, I think, and I read, if I recall properly, some of the presidential election polls they have only involve a couple hundred people. So the idea of sampling is to select a portion or subset of the larger population and study the portion and sample to gain information about the population. So data are the result of sampling from a population. Here's some examples. Or you can think of examples. You can read the textbook to see what they have. So there's 2 things. There's something of interest that we want to study in the population. So if we're looking at the population of all voters in the United States, or the people that are most likely to vote, the parameter we're interested in is the percentage of that population that's going to vote for candidate A or candidate B. Now, that's a parameter. We call it a parameter. That's what we want to study. If we went to every house, knocked on the door, and got everybody's information, so that would be the parameters measurement at that point. But if I take a sample of 200 people and I say who's going to vote for candidate A, we call that a statistic. Does the statistic represent the parameter, and how well does it do that? Well, of course, the accuracy of the estimate depends on how well the sample represents the population. When we're talking about voting, we know that by zip code, you can move from strongly Democrat to strongly Republican to mixed to whatever. I mean, if I just think of where I live in Lake Forest, Illinois, 60045, and Albany Park, whatever the zip code is there, where North Park is, I think Lake Forest is going to be somewhat more Republican. Albany Park is going to be probably even markedly more Democrat. So if I choose my entire population from just one of those two places, if I only choose men, if I only choose women, if I only choose people over 30 or over 40 or over 50, and don't represent the voting population properly, will I get that representation? Will I get a good inference? Will my statistic be a good inference of the population parameter? So setting up a population or a sample is very important. How you do it and how you make sure that it's random and also represents the general population. So one thing we talk about is variables. We denote these by capital letters. We use the usual suspects, X and Y and Z and things of that nature. Characteristics of interest for each person or thing in a population. So if I'm looking at, let's say I've got incoming college students, and I'm just trying to collect data on the weight of male college students, the weight of female college students. So my population is all male college students entering college in 2021. What's the distribution of their weight? The variable I might use is a capital W. So variables can be numerical or categorical. What does that mean? What if I also looked at eye color? Weight is a number, right? You're going to weigh 150, 175, 200, 201, 168, 188. You know, these are all numbers. When I have numbers, I can add them up. I can take the average and such. So those are called numerical variables. Take on values with equal units such as weight in pounds or time in hours. Categorical variables are something else. Let's say I look for, I just want to have understand what's the eye color of incoming college freshmen in the year 2021. Well, eye color is, blue, brown, hazel. I don't know. There's a small portion of the population that has violet color of the eyes. There's a small segment of the population that each eye is a different color. So I think you have like 4 or 5 eye colors at most. Sometimes there's even dark brown can be considered black. Not real sure. But I can't take the average eye color. I can't add up all the eye colors. I can't add up brown and blue and black. But I can tell you which one occurs more often, which one occurs second most, and the percentage of occurrence. So I can translate that into something. I mean, you understand how we can take a categorical variable and make it a numerical variable where it makes sense. You do it all the time and just don't know you're doing it. Or it's done to you all the time and you don't know you're doing it. For example, grade point average. It's a categorical variable. Grades are categorical variable. You get an A, you get a B, you get a C, you get a D, or you get an F. We're not counting the I's and the W's and all that stuff. We're only talking about grades for people that finish the class or were registered when the class ended. Because oftentimes people get F, don't actually finish the class. They just drop out without dropping the class. The fairness of that is a whole different issue. But in order to get an average grade, I can't add up A plus B plus C and divide by 3 if you only have 3 classes. So we assign a number. A is a 4, B is a 3, C is a 2, D is a 1, F is a 0. Now if I have the number of classes that I got A's, B's, and C's, if I had a class with A, B, C, I add 4 plus 3 plus 2, which is 9, divided by 3. The average grade is, not surprisingly, 3.0, which is a B. So data are actual values of the variable. They may be numbers or they may be words. Datum is a single value. Like blue for eye color, which is a categorical variable, is a datum. Now the only time you ever see datum is on a slide like this in an introductory statistics class. Most of the time, the rest of the world calls it a data point. it comes from Latin. Datum is a single point of data. Data is a plural of datum, which means all the data that you've collected or are about to collect. But over time, we've lost that designation or the distinguishing characteristic, and we talk about data as being the data we collect, and a data point being the equivalent of a datum or one point. Here's an example. Determine what the key terms refer to in the following studies. We want to know the average mean amount of money first-year college students spend. And notice that average and mean are interchangeable. Spend at ABC College on school supplies that do not include books. We randomly survey 100 students at the college. 3 of these students spend $150, $200, $225. What's the population? Well, it's all first-year students at ABC College. What's the sample? The randomly selected 100 first-year students. This is assuming ABC College has more than 100 students. If not, it's the population. What's the parameter? We want to know the average amount of money students spend on school supplies that do not include books. The statistic is what those 100, the average based on those 100 students. So if we look at 100 students, what they spend on books or on school supplies, not including books at ABC College, and take the average of that, can we extend that to the entire population? I would say I would probably could do that without really worrying about it much. 3 of these students spend $150, $200, and $225. So the variable we're looking at is the mean. The variable we're looking at is money spent on school supplies that do not include books. The data that we only have here are 150, 200, 225. Those 3 data points, if you will, are only 3 of the 100 data points. The 100 data points that were collected. Another example. Determine the key terms referred to in the following study. A study was conducted at a local college to analyze the average cumulative GPAs. By cumulative, it means all classes that you took, of students who graduated last year. A study was conducted at a local college to analyze the average cumulative GPAs of students who graduated last year. Fill in the letter of the phrase that best describes each of the ones below. What's the population? All students who attended college last year? No, we only want students that graduated from college last year. So the cumulative GPA, no, that's not it. Those 4 data points, no. A group of students who graduated from college last year randomly selected, no. The average GPA of students, no. All students who graduated from college last year. That would be the population. Even though it's not clear in the words, sometimes words and definition of population, you got to be a little careful. A study was conducted at a local college to analyze average cumulative GPAs of students who graduated last year. Graduated only from that local college, or graduated from all colleges in the United States or all colleges in the world. I'm still going to go with F. That's the best explanation of the population. Well, a statistic is a group of students who graduated from college last year randomly selected. That's my statistic. What's my parameter? The cumulative GPA of all students who graduated from college last year. That would be E. The sample would be the average GPA of students who, let's see, the average GPA graduated from college last year. Oh, the average GPA of students in the study who graduated last year. That would be the sample. What's the variable? The GPA of each student. The cumulative GPA of students that graduated from college last year, that would be E. And the data, example of data points would be C, if that's what I collected. Go through this yourself and see if I made any sense at all. You may have to do something like this on an exam, like exam 1. Determine what the key terms refer to in the following study. Okay, an insurance company would like to determine the proportion of all medical doctors who have been involved in one or more malpractice suits. The company selects 500 doctors at random from a professional directory and determines the number in the sample who have been involved in a malpractice suit. What's the problem? What's the population here? All medical doctors or all medical doctors who've been involved in a malpractice suit? That's what we want. The sample, they're going to select 500 of those doctors, and I don't know, maybe I don't know the number of doctors that have been involved in a malpractice suit, but I can find 500 doctors in a random sample from a professional directory and determine the number in the sample who've been involved in a malpractice suit. Can I guess my proportion out of 500 to that? So my population is all medical doctors. My sample is 500. The parameter I'm looking for is proportion of doctors. That would be doctors that had a malpractice suit divided by the total number of doctors. The statistic is the number of doctors out of the sample of 500 that have been involved in a medical malpractice suit divided by 500. The variable is yes or no. It's a categorical variable, or 0, 1, which is usually the way we would make it numerical. 0 if you've not been involved in a malpractice suit, 1 if you have been. And the data will be for each particular doctor, are they a 0 or a 1? That collection of 500 zeros and ones would be the data. Okay, so data sampling and variation in data and sampling. So there's two types of data. We talked about numerical and categorical in terms of variables. Can be numerical or categoricals. And when we look at the data, which are obviously categorical variables, tend to be qualitative, are the results of categorizing or describing attributes of a population. It's the same thing: hair color, blood type, ethnic group, the car a person drives, etc. Quantitative data types are always numbers, and the numbers mean something. Quantitative data are the results of counting or measuring attributes of a population. Amount of money, pulse rate, weight, number of people living in your town, the number of students who take statistics, how much they spend on books, blah, blah, blah. Quantitative data can be either discrete or continuous. Discrete doesn't mean it can keep a secret. Discrete means something else. Usually when you look at the possibilities of data points, you would pick two data points. Like, let's say the height of a person. They could be 5 feet tall or 6 feet tall. In between 5 feet and 6 feet, there is essentially an infinite number of heights, only limited by the number of decimal points in inches that you're going to, or in feet that you're going to go to. So if I have a really sophisticated measuring device that can go out 14 data points, there's a seemingly uncountable number of data points. That would be called continuous data, right? So if you're talking about measuring the height of athletes in centimeters, that might vary between such numbers as 172 to 191. But I can have anything in between, and I'm only limited by the precision, how many decimal places I go to, of the measuring device. That's a continuous data. There's infinite, between any two data points, there's the possibility of infinite measures. Now, counting numbers. How many books do you own? Well, those are going to be a counting number. So if I have 10 books or I have 5 books, in between 10 and 5, 10 minus 5, there's only 4 things, right? It could be 6, 7, 8, 9. I can't have, I suppose I could rip books in half, but that wouldn't be considered a book anymore. That would be considered trash. So when we're talking about how many books do you own, it has to be a counting number. So between any two data points, there's only a finite number. That's what makes it discrete. It's more counting numbers. Things that you can measure, if we're talking about centimeters, between 180 and 190 centimeters, there's only 9 points, 181 to 189 if you round everything off to that. But it's still a continuous measure because I have to know in my head that I could use any fraction of that, and it's just based on how I want to report the data. The possibilities there are countless. Okay, so try it. The data are the number of machines in a gym. You sample 5 gyms. One has 12, one has 15, one has 10. And notice this. This is typical professorial nonsense. 12, 1 written out, 15, 1. You know, they rate 10 here and 22. So you got to be very careful when you read story problems, because that's a professorial curveball to sometimes write the number out and sometimes express it as a word. What type of data is this? If we're talking about number of machines in a gym, it's definitely discrete. It has to be a counting number. The data are the areas of lawns in square feet. You sample 5 houses. The lawns are 144 square feet, 160, 190, 180, 200 square feet. It looks like it's a counting number, but you know that if I measure it, I could have, if it's a square lawn, I could have 10.2 feet by 11.7 feet. Or it's just really how precise I want to be on the number of decimal places I have. That's continuous data. The colors of houses, it's definitely categorical data, and so it's qualitative. The first two are quantitative. First one, quantitative discrete, quantitative continuous, and this one's qualitative. All right, so work collaboratively, do this on your own. We can go over it in class if anyone wants to. Work collaboratively to determine the correct data type. Indicate whether quantitative data or continuous or discrete. Data that are discrete often start with the words the number of. The number of the pair of shoes you own. Well, thanks for the hint. OpenStax, let's call that discrete, quantitative discrete. Type of car you own, that's categorical. Where you go on vacation, that's not a number, it's got to be a place, right? So it's going to be, Palm Beach, or it's going to be Galena, or someplace, Hawaii, however you do it. The distance from your home to the nearest store. Oh, that's miles, but it really depends on, most cars will measure it in tenths of miles. There's going to be 6.4 miles, but really it's only limited by the precision of the measuring device you use. It could be 6.43 or 6.43721889. Oftentimes for a continuous variable, if you show 8 decimal places, I will ask you, do we need 8 decimal places for this data? The only time you really need 8 decimal places is when you're flying rocket ships to Mars. And the 8th decimal place may be the difference between landing safely on Mars or singing the Major Tom song that we all know about. I'll let you go through this yourself. Now, a statistics professor collects the information about the classification of her students as freshmen, sophomores, juniors, or seniors, and the data is summarized in this pie chart. They call it a pie chart because it's round and it has slices that depict the proportion of each category. And pie charts are pretty good for categories. What does a graph show? Well, most of the people in her class are freshmen. And overwhelmingly, most are freshmen and sophomores. Juniors and seniors have put off the class as long as they can, but eventually have to take it because it's probably required. And you'll find that's the case in statistics. I find that in my operations management class in the School of Business. I have a couple seniors every time, and I'm like, why did you wait so long to take this 2,000 level course? And they were just putting it off. I guess I have a scary reputation. Tables are good, but tables, when you just glance at it, you have to study the data a little bit. You have to look at the numbers and glean what you're getting from it. This is real clear because remember, a picture is worth 1,000 words. I like to have tables and graphs together. So this is, tables are a good way of organizing and displaying data, but graphs can be even more helpful. Here's two colleges, De Anza and Foothill. We're talking about the full and part-time professors. I'm guessing you don't have 9,000, you don't have 22,000 professors or 14,000 professors. It must be students. Here's something that's unclear. You have to put in the title of your data what it is. Full-time students enrolled in college. Okay, so you have De Anza College, Foothill College. And if you look at the percentages, you could look at the numbers, but there's more, you could conclude from the numbers that there's more people at De Anza College than at Foothill College. Certainly there's more part-time students at De Anza, but when I look at the percentage, it tells me as a percentage of students, they only have 60%, and at Foothill, there's 70% part-time, and the full-time students at De Anza are 40%, and the full-time students at Foothill are 28%. So De Anza is closer, has more full-time students as a percentage, and Foothill has more part-time students as a percentage. That's what you can glean from this. Another way of looking at it is if you look at this proportion, it becomes very clear the difference. Part-time students at Foothill are much larger than part-time students at De Anza, and the proportion of full-time students at De Anza are less. So I would probably have both. I would present both. I would have this and I would have this. And if it's a PowerPoint, I might just show this, but if it's a report, I might provide this and this. Bar graphs are another way. Here's one way of looking at it. You can look at the proportion of students. First of all, you can see that the number of students at Foothill is less. So this gives you something that the pie chart didn't. It also tells that in each case I have less students at Foothill. But it also says that you can see clearly that the proportions are different. Not as clearly as in a pie chart, but you can still see it. And the numbers are listed there, on there. I would put commas in to signify the thousands. It's just easier to read. Now there's something called a Pareto chart. It's organizing charts from largest to smallest. Pareto chart means something very specific in quality control and quality engineering. We can talk about that a little bit more when we get to it. But what it's showing is if you have this categorical variable and you're saying the ethnicity of the students, whatever school this is, you're going to find out that you have a majority of your students are Asian. Then you have the white students are only 24%, and Hispanic and Black and Filipino, etc., and other unknown is about 10%. One thing that you could say is, do we want to get a better classification of this data? Can we make the categories easier for people to pick something other than unknown? But there's a small, probably 10% of the population looking at this chart, or 10% of the population at this school that just don't, why are you asking me this? This is dumb. I refuse to disclose my ethnicity. But if you're thinking about how to cater to students, who are you catering to? You want to definitely cater to all the students, but if you're going to focus on an ethnic group for any reason, it's going to be Asians, or Asians, white, and Hispanics. That makes up what percent of your school? That makes up 50.6, 67.7% of your students. Over 2/3 of your students are Asian, white, and Hispanic. Does that mean you leave out the blacks and Filipinos? And why wouldn't Filipinos be Asian? Why are they separate? I don't know. But if you add that to Asian, you're at over 40% Asian. And that might help you guide your policy. And maybe you might look at this and say, we need more black students at our school. How can we get more black students? If that's something that you want to glean from this data. Or it might be, how can we make sure that we, North Park became a Hispanic serving institution because I think you have to have 25% Hispanic students. And once you cross that threshold, and put certain programs in place, you can get federal or state aid in that regard. So some of these things are important from a funding standpoint. Okay, sampling. We talked about the presidential election, and we talked about my zip code where I live and the zip code at Albany Park. So if I only go and I'm going to sample 200 people to try to predict who's going to vote for candidate A or candidate B, and I only picked all 200 from Lake County, Illinois, or 60045 Lake Forest, Illinois, I'm probably going to get a misleading statistic on the proportion of people voting for candidate A and B, because it's more affluent and more Republican, probably. If I go to Albany Park and do the same thing, I'm going to get a more Democratic answer, because the zip code is less affluent and more Democratic. What if I have a disproportionate number of males and females, disproportionate number of white people, blacks, Latinos, whatever you want to say? If I have disproportionate, I have to reflect the population. So and I can't have people only from Illinois. I've got 50 states. So I have to have people from all over. I've got to have roughly 50% Republicans, roughly 50% Democrats, roughly 50% men, roughly 50% women out of 200. If whites make up, let's say, 50% of the population, that's it. I want 50% of the population, that sample should be white. If I have, let's say black and Latino populations are 20 and 20% each, and I'm just making it up because I don't really know. 20% of that population should be black and Latino. If I'm looking at sexual preference, should it be heterosexual, gay, homosexual? Does that matter? If that's a factor, I want to reflect that. Age is probably important. I probably want to have 20 to 29-year-olds, 30 to 39-year-olds, etc., reflect that proportion in the population. So something like for a presidential election is pretty darn important. If we look at something like, what's the grade point of all students, and then they have to look at the cost of getting this data and going out and finding these people. So oftentimes, if I'm just doing a quick and dirty calculation and it really doesn't have a lot of consequences, and I want to find out how much do college students spend on school supplies, I could just survey my class. And is that going to be good enough for what I'm trying to determine? Well, if I'm Amazon and I want that answer because I want to know what kind of school supplies to stock, well, Amazon already has that. Whoever ordered from them last year, they already know all those proportions. And they just have to decide whether they want to order more or less. And if you look at over time, they could look at then the trend and see. So anyway, a sample should have the same characteristics as the population is representing. I think I beat that to death with the candidate A, candidate B presidential election. So most statisticians use various methods of random sampling in an attempt to achieve this goal. An attempt. They didn't say in a guarantee to achieve that goal. And there are several different methods of random sampling. The first one we're going to look at is simple random sampling. Each sample of the same size has an equal chance of being selected. So if I'm looking at 200 people, I put all registered voters into a veritable hat and choose 200 of them randomly. Well, do you think I'll get a random population? Sure, because that if I put it in a population and mix them all up and somehow change the order, I alphabetize their names or something like that, and I rank order them by age or something, or however I do it, or I just assign them a random count number and pick 200 of them out of a hat. Will I get the right proportion? You have to look at it and see, but you probably will. There's other ways of doing it. There's something called a stratified sample. Divide the population into groups called strata, and then take a proportion of each one. So I know if I take that same list of all registered voters and separate it into men and women, I separate it into various age brackets by, basically I make a big spreadsheet of all these things, and I know what the average proportions are for each of those cells. I can pick X number of people from each of those cells and have a pretty good random sample. For example, you could stratify your college population by department and then choose proportionate random samples from each strata, each department, and get a stratified random sample. So if I have business, healthcare, nursing, liberal arts sciences, liberal arts humanities, let's see what else we have. School of Education, so we're just looking at undergraduate stuff. And I know what the population of each of those schools are, and I want to take some random number of students or professors. I could choose from, and I need, say, from business, I want to pick 2, from Haas, which is history, arts, and social sciences. I have to pick 10, and from sciences, I have to pick 3, and from nursing, 5, and from education, 1, perhaps. I'm just making up those proportions. That would be a stratified sample. A cluster sample is divide the population into cluster groups that are randomly selected into clusters. All members of these clusters are in the cluster sample. For example, if I'm looking at 4 departments from your college, the 4 departments make up the cluster sample. So a stratified sample and a cluster sample are somewhat the same. Another word of looking at cluster, let's say I want to I have an apartment building and I want to, I don't want to sample all 500 residents, but I really want to, I want to make it face to face. So I'm going to look at a sample of 30 residents, and I want to go door to door and knock on their door and have an interview with them. And maybe I'm going to do it this way. The people I choose to do it, I don't want to be going all up and down the building, all different floors. So I'm going to I want 30 people, and the building's 30 stories tall. Maybe I pick 5 floors and collect 6 people from each floor. That would be a clustered sample. And they overlap somewhat. The way they've written their example of using departments for cluster and a department for stratified is a little confusing. So other well-known methods are something called systematic sample. So selecting a starting point and taking every nth. So in other words, if we're in a classroom and I have people sitting together, and if I want to break you into samples of 5 and there's 30 people, I'll have you count off by 5s. Well, that way I'm breaking up people that know each other, and I say, okay, all the ones, count off by 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, going around the room. And I say all the 1s come up here, all the 2s meet in the back, all the 3s meet here. Immediately I've set up kind of a randomly sampled, it's a systematic way of randomizing 6 samples of 5. And the other one is convenience. Sampling data should be done very carefully. Collecting data carelessly can have devastating results, but surveys mailed to households and then returned may be very biased. They may favor a certain small group. But, this day sampling is tough. You can't just call people because people don't answer their phones. The only people that tend to answer their phones are older people that with house phones. Everybody on the younger side of things, they see a random number that they don't know ring on their cell phone, they're not going to answer it. How many people get surveys through the mail? Like 1-2% of the people answer those? And oftentimes they're people with extreme opinions. So you got to watch out how you use convenience. For me, convenience, if I want to make a study at North Park and I have a class that I think is representative enough, and a statistics class is great because so many majors require statistics that I should have a good mix of students in my statistics class. And we probably have some freshmen and sophomore, lesser junior and seniors. I would just pick my one class. I don't have to go around. I've got a captive audience. That would be a convenient sample. I've just got to make sure that I'm not trading off convenience, so much for convenience that I increase the bias of my result. What else do we have? There's other ways of sampling. Sampling with replacement, sampling without replacement. Well, most sampling, once a member is picked, the member goes back into the population and may be chosen again. I don't think that's used very often. And because you don't want to pick the same person a couple, 2, 3 times. But a member of the population may be chosen only once. So you pick someone, then you pick someone else. If you think about cards, if I replace a card, what's the probability of picking an ace? 4 out of 52. If I replace a card, what's the probability of picking and shuffle it again? What's the probability of picking another ace? 4 out of 52. Without replacement, the probabilities change. What's the probability of picking an ace? 4 out of 52. I don't replace the card. What's the probability of picking an ace the second time? Well, it's 4 out of 51 because I took a card out if the first card was not an ace, or it's 3 out of 51 if the first card I picked was an ace. So you see there's that subtle difference that occurs with and without replacement. I don't know of any sample for elections. I'm going to just go out on a limb and say most sampling is done without replacement. I'm trying to think of an example where I might sample something with replacement. All right. So when you analyze data, it's important to be cognizant of sampling errors and non-sampling errors. Well, what's the actual process of sampling causes sampling errors? The actual process can cause errors. For example, the sample may not be large enough. The sample may be biased, as we talked about. The factor is not related to the sampling process causing sampling errors. A defective counting device can cause a non-sampling error. So in statistics, the sampling bias is created when a sample is collected from a population and some members of the population are not as likely to be chosen as others. When a sampling bias happens, there can be incorrect conclusions drawn about the population that is being studied. And you have to be cognizant of this and maybe run the test a couple, 2, 3 times if you can afford it. So there's always this balance of ease of collecting the data and the cost of collecting the data. You want to be as random and representative of the population in your sample as possible, but you don't want to spend gobs of money to do it. So that's the game, that's the basic underlying game in sampling. Determine a type of sampling used, and the simple, random, stratified, systematic, cluster, or convenience. A soccer coach selects 6 players from the boys aged 8 to 10, 7 players from a group of, well, you can already tell that's stratified. He's stratified it by age. A pollster interviews all human resources personnel at 5 different high-tech companies. All human resource personnel at 5 different high-tech companies. That would be if the population is all human research people at all high-tech companies, this is a cluster sample. He's saying, I'm only going to go to 5 companies, but I'm going to interview all the HR people there. A high school education researcher interviews 50 high school female teachers, 50 high school male teachers. That would, I think, I'm going to say, is, what was systematic? See, starting point, we didn't take every nth one. We didn't do that yet. So this would be probably clustered. Medical researcher interviews every 3rd. That's systematic. A high school counselor uses a computer to generate random. That's simple random. A student interviews classmates in his algebra class to determine how many pairs of genes students own on average. That is a convenient sample because you've got a captive audience. All right. So we need to evaluate the statistical studies we read about critically and analyze them before accepting the results. You have to look at the underlying sample and make sure it's representative and not biased. Biased samples are not representative of the population, give results that are inaccurate and valid. I'm sorry, I think my wife is opening and closing the door. Self-selected samples. Responses only by people who choose to respond. Call-in surveys, emails, all that stuff. They're saying it's often unreliable, but sometimes that's all you can do, and that's all you can get. Remember, it's the convenience, how much you're going to pay to get the sample, and how much feedback you're going to get. So you have to be careful in the conclusions you draw. Sample size issues. Sample sizes that are too small may be unreliable. Larger samples are better if possible and if cost effective. In some situations, having small samples is unavoidable, but can still be used to draw conclusions. Crash testing cars is really expensive. So this would be, you can't test the same car twice. That's where replacement and without replacement. If in reliability, I should have thought of that. I used to be a reliability engineer at a point in my career. If you test something and you don't destroy it, you can test it again. But if you test something to destruction, you can't test it again. So that's without replacement. That is with replacement. And reliability is a specific place where that makes a huge difference. And if you test things to failure, in other words, you test things to catastrophic failure, you've lost that item. And if they're prototypes, they're very, very expensive. Okay, critical evaluation. Continue with that. Undue influence, collecting data or asking questions in a way that influences responses. Non-responses, or refusal of a subject to participate. We give that option when you ask for race on many forms. Other or refuse to respond. So we saw in that one Pareto chart there was like 10% of the responses were that way. The collective responses may no longer be representative of the population. Often people with strong positive or negative opinions may answer the survey, as we talked about before, and that can also affect the results. Can I evaluate my company on the 800 calls? Well, people that call 800 numbers are usually really upset and don't like you or with your product. And that's probably, I'm going to say that's like, let's say that's 50% of the calls. Maybe another 20% of the calls are people that are really happy and they just love what it's so great, I had to call. And then the other 30% are people that just have random questions. So if you use 800 number calls for anything about other than customer complaints, you're biasing it heavily by the overwhelming customer complaints. The other thing is there's a relationship between two variables. Does not mean one causes the other. As we talked about in class, when there was the polio epidemic in the 1950s, for a short period of time, people were wondering if dairy was a cause of polio because polio occurred in the summer, and as the polio rates increased each year, so did ice cream consumption. So cold dairy consumption, was there something in ice cream that perhaps caused polio because there was a high correlation? They followed the same exact shape if you graphed it over the course of a year, month by month. Number of polio cases, ice cream consumption. Well, it's not the case because polio was caused by, I think, a bacteria or a virus or something in the water. People went swimming more in the summer. So it's always good to have what Walt Disney said, is at least one person on a team that knows what the heck they're doing. You need a subject matter expert. Correlation in itself does not, you can't draw the conclusion of causality just from correlation. It would be like, we see a relationship between people that smoke 1 pack of cigarettes a day and the incidence of lung cancer. Well, the correlation is there. You can take the correlation two ways. Smoking causes lung cancer, or people that have lung cancer have a proclivity to smoke. Well, we know that that's silly. It's a first. But the reason that we drew the conclusion from the first is the correlation led biologists and chemists and biochemists to study what happens at the cellular level with the tars and nicotines in cigarettes that cause the cells in the lungs to metastasize and become cancerous. Once we establish that causality scientifically, the correlation leads to causality. Be very careful with this. People always jump to causality. I've seen it too often, especially in industrial statistics and quality management. Okay, self-funded and self-interest studies. Well, you know, how often do you see this thing that says, you know, the most livable city in the United States is, or the happiest place to live in the United States, or the best place to live in the United States is, you know, city called Podunk in the state of someplace, right? And then you read in the fine print that, you know, wow, I never would have guessed it would have been the most livable place or best place to live. But then you read the study was sponsored by the Chamber of Commerce of Podunk. Well, duh, of course that's going to happen. You know, what's the best tasting apples in the world? Well, they're Fuji apples grown in Washington. And a study was sponsored by the Apple Growers Association of the state of Washington. Gee whiz, really? So, you know, you can a study performed by a person or organization in order to support their claim. That's a self-funded or self-interested study. Be careful. Is the study really impartial? Read the study carefully. Most people, you know, don't read the fine print to find out how they did the study and what the sample was. So you can't automatically assume the study is good just because it's printed, right? What's the old saying? Don't believe everything you read on the internet. And they attribute the quote to Abraham Lincoln. Well, there was no internet when Abraham Lincoln was there, so it's kind of funny. Evaluate it on its merit and work done. Most people don't do the digging to find that out. Misleading use of data, improperly displayed graphs. I mean, you can show differences or no differences if you expand or contract the range on the y-axis, and we can show how that works at some point in class too. And then you have this idea of confounding. When the effects of multiple factors on a response cannot be separated, confounding makes it difficult or impossible to draw valid conclusions about the effect of each factor. And what does confounding mean? Confounding is the interaction of factors, right? Does humidity itself make it rain? No. Does air pressure itself make it rain? No. But the combination of high humidity and low air pressure, or high air pressure, I don't know which, you can predict rain much better if you look at that. High, medium, low humidity, high, medium, low air pressure, where is precipitation most likely? And then if you might even throw temperature in there, so you have three factors and they all interact. So maybe only with two factors and three choices, high, medium, low, you have 9 possibilities, and not all of them, you know, some of them cause rain, some of them cause dryness, some, you know, whatever. You can look. If I throw in temperature on top of it and make it high, medium, low temperature, if I'm going to categorize the temperature, now I have 27 different squares. I've got to look at the confounding. People don't see confounding easily. It sometimes requires experimental design to do that. So, frequency tables. So we're going to have a separate video on some of the data that we collected in class and how to put it into a frequency table. Carry your final answer to 1 or more decimal place than was present in the original data. Round off only the final answer. Do not round off by immediate results if possible. Excel rounds off anyway. I wouldn't worry about it for the stuff that we're doing. Level of measures. We can classify into 4 levels of measurement: nominal, ordinal, interval, and ratio. This is levels And let's take a look at this. A nominal. A nominal scale is called qualitative. It is categorical. So we've used the same word. Now we have the word nominal, we have qualitative, and we have categorical. They all kind of mean the same. These are the color names, labels, things that you can't take the average of. Nominal scale data are not ordered. They can be ordered, but alphabetically, and the order doesn't mean anything. For example, people trying to classify people according to their favorite foods does not make any sense. Like putting pizza ahead of sushi is alphabetical, but it's not meaningful. I have to look at the number of people that prefer pizza and the people that prefer sushi and make a conclusion based on that. Ordinal is the next. It's similar to nominal, but there's a big difference. Ordinal scale can be ordered, hence the word ord. An example of an ordinal scale is the top 5 national parks in the United States. If I ask you to rank the top 5 national parks in the United States, can be ranked from 1 to 5, but I cannot measure the differences between the data. Interval scale. Data that's measured using interval scale is similar to ordinal because it has a definite ordering, but there is a difference between a data. Difference between interval scale data can be measured though the data does not have a starting point. Well, this is mostly temperature. Temperature is a relative, Celsius is 0 Celsius is what? Where water freezes. 100 Celsius is where water boils. And Fahrenheit are measured by something different. In both measurements, 40 degrees is equal, the measurements 40 degrees Celsius is equal to 100 degrees minus 60. Differences make sense, but 0 degrees does not, because in both scales, it's not the absolute lowest temperature, it's a relative scale. So it's an interval scale. Is it twice as hot if you go from 25 degrees Fahrenheit to 50 degrees Fahrenheit? Well, you could say it's twice as hot. But if you go from 25 degrees Celsius to 50 degrees Celsius, it seems like it's 10 times as hot. It's not twice as hot. So that doubling does not make a difference. Whereas in something like weight or height, if I weigh 100 pounds or I weigh 200 pounds, that's twice as heavy. If I'm 5 foot tall or I'm 10 feet tall, that's twice as big. But these are relative scales. And temperature is the premier example of that. A ratio scale is the ratio, takes care of the ratio problem and gives you the most information. Ratio scale is the interval scale, like an interval scale, but it has a 0 point and the ratios can be calculated. For example, for multiple choice statistics final exam scores out of 100. The data can be put in order from lowest to highest. The differences between the data have meaning. The score 92 is more than the score 68. If you scored 50% on the test or you scored 100% out of the test, and it's a ratio. Right answers divided by wrong answers. Right answers divided by total answers, total possible answers, total questions. So I'm giving you 100 points on a test, and everything that I give you half the credit for each question. You're going to get 50 out of 100. Someone that gets 100 out of 100 did twice as well as you did on that test. So ratios can be calculated. The smallest score is 0. So 80 is 4 times 20. The score of 80 is 4 times better than 20. Where I can't say 80 degrees Fahrenheit is 4 times hotter than 20. And I can't say the same thing if I go 80, because when I say 80 degrees Celsius, 4 times hotter than 20 degrees, it has a different, people will not agree. They'll think 80 degrees is 100 times hotter than in Celsius than 20 degrees. All right, so frequency tables. The mean height of all students. Frequency is the number of times a value occurs. The relative frequency is the ratio of the number of times a value occurs divided by the set. And I'm going to have, like I said, a separate video on creating these. To find the relative frequency, divide each frequency by the total number of students in the sample. N. equals the sample size, small n. Capital N would be the size of the population, if you know it. Cumulative relative frequency is the accumulation of previous relative frequencies. Again, I'll have a separate video that shows how that works. So now we have experimental design. If you're trying to collect data, the purpose of an experiment is to investigate the relationship between two variables. When one variable causes change in another, we call the first variable an independent or explanatory variable. The second variable is called a response variable. So in other words, if I have, or in a randomized experiment, the researcher manipulates values of explanatory variable and measures the result changes in the response. These different values of explanatory and variables are called treatments. The experimental unit is a single object to be defined as a measurement. So we have observation versus experiment. We have examples, lurking variables, or assignment, random assignment to treatments. And let me pull up Excel here a little bit and just show you something. If I can do that. Okay, here's my Excel. Let me make it a little bit bigger so you can see it, so I can explain what an experimental design is. What are we trying to do? Let's say we have, I want to test to see if water and fertilizer, a lot of experimental design was developed for agriculture. So here we go. I can water, however I define it, as low, medium, and high. Okay? I can, and I gotta add another column in here. I can fertilize at a low, medium, and high level. So let me expand this across. How much water I use, how much fertilizer do I use, and okay, so I got this, right? And basically I have 3 times 3. I have 9 parcels of land in which I'm going to plot maybe the same crop, right? So I've got, let's say I got this. Let's insert borders. Let's insert borders. Let's insert borders here. Now I'm cooking with gas, right? Let's make this bold. And I'm going to make it look pretty. Remember I said you'd always make things look pretty. So let's make this powder blue. And let's make this, I don't know, powder green. Okay? So now I've got this. And let's say I've got 2 acres of land in each parcel. One I'm going to use low fertilization, low water. One I'm going to use low fertilization, medium water. One low fertilization, high water, and go on and on. And I plot, let's say the crop is, what should we say, corn? 2 acres each. And what else do we want to say? What's my explanatory variables are water and fertilizer. Dependent variable is yield in, I don't know, bushels could be one measure, or tons might be another. Which one? Pick one. So then I would take this land and I would decide where I'm going to, the 2 acres I've allocated for each of these, and hopefully I've assigned them kind of like randomly out of a plot of, and so it's 2 acres each, so I got 18 acres I'm dedicating this. Let's assign them all randomly, and I plot the corn, and then I start looking at what the yield is. And you're going to find some combination of water and fertilizer pop and show you more. Maybe it's medium water and high fertilizer, or maybe it's medium fertilizer and high water. I'm going to guess might be the answer. But this would be an experimental design. And this is how you would set it up. You'd collect it, and then how do you analyze the data to see if there's any differences between the levels of water, the levels of fertilizer, and if there's any interaction, if there's any confounding amongst the two variables. Okay. So we just gave an example of that. You can read lurking variables in the textbook. I probably won't test on it. So when a participant, they talk about blind studies. In a study prompts a physical response from a participant, it's difficult to isolate the effects of the explanatory variable. So sometimes they use a control group, and they did that. The control group, especially in medical cases, they're given, they have one group that's given a pill, but it's just a placebo. It's a tic-tac, and the other one actually gets the pill. And they try to see if the people taking the pill have any difference from the people that just took a tic-tac, that they call a pill. So blinding in a randomized experience preserves the power of suggestion. When a person involved in a research study is blinded, he doesn't know if he's receiving the active treatment or the tic-tac or the placebo. A double-blind experiment is when both subjects and the researchers are blinded. So you don't know what you're giving to each, but you have to know when you get the data back, or else you'll never draw a conclusion. Sometimes when you grade essays in something for college admission and all that, they don't include the person's name or ethnicity or all this stuff, so that biases are taken out, and you're just grading the essay for the sake of the essay. But then, of course, the number assigned, your grading number, student number 1, 2, 3, 4, 5, and you tested it, and then you find out later that the student's name, when the admissions people get the grading from you. So you'd like to have my evaluation of entrance essays be blind, so that you're not biased by the person. And I think that's it for this lecture. Look for also a video on putting together a frequency table like we did in class. Thank you very much, and look for more videos.